Okay, shall we start now? Yeah.
Recording in progress.
Okay, this is the presentation 2. First part is actually the for optical remote sensing part, what is remote sensing and how we come into the microwave remote sensing. Okay, in this one we are going to do the what is called the imaging radar because of there are non-imaging radar as well, because of the radar system is using the microwave, and there, yes, is it clear? Hello, sound is clear?
Yes, sir.
Okay. There are two kinds of radar system. Radar, because of the radar is coming from somehow from the microwave. Why we are using the microwave? By using microwave, we are making the image as well as there is a non-imaging part as well. Okay, however, in this microwave remote sensing part, we are doing the imaging radar instead of the non-imaging radar. Okay, however, we can describe now what is imaging and what is non-imaging radar. Okay. Okay, this is what is radar first. No? Before going to the non-imaging and the imaging radar, this is a radar system is also the electromagnetic sensor used for detecting, to identification, locating, tracking and recognizing objects of various kind of objects at considerable distances. This is the remote sensing. We are using the sensors to detect, locate, tracking and recognize the object. All are the remote sensing. Okay. It operates by transmitting electromagnetic energy towards the object, that is the target, and observing the echoes, that means the reflecting part, which is coming back to the sensor, that is the return to the sensor, and recording. Okay, this is how the radar is operating, because of the transmitting electromagnetic energy towards the object or the target and observing the echoes. This is the reflected one returning from the object, from the target. Okay, this is what is the radar is doing. This electromagnetic energy they are generating itself and send it to the object, send it to the target. The radar is coming from the acronym, the radio detection, because of we are using the radio waves. I will explain what is the radio wave and what is coming from the microwave. The radio detection, detecting the object, and ranging means locating. That means the finding out the distance. Finding out the distance. After finding out the distance, we can locate the object. So that this radar is coming from the acronym, because we are using the radio wave to detecting object, and ranging means finding out the location. That means finding out the distance from the object to the sensor. Object to the sensor. That is what we are doing in the radar system. We are using radio wave, that is the part of electromagnetic spectrum. The relevant sensors are using, which has the ability to detect the radio waves. In optical system, you have the sensors which have the ability to detect in different part of the visible range as well as the infrared part. This is the optical system. But these sensors these sensors have the ability to detect the radio waves. As well as the sensors are transmitting and sending the radio waves to the ground, to the object, and the same sensor is detecting which is reflecting from the object. That is the echoes coming from the object. That is what we are doing in the radar system. How it is happening is, this is the sensor or the transmitter as well as the receiver. Both are same. Red part is sending to the radio waves to the space, and if there is object and touching with the object and reflecting back, part is reflecting back to the sensor or the transmitter. But when the sending the microwave from the transmitter, this is given in the all radial directions. All radial directions are using to send this microwave, because of this is going as a curve, means is going everywhere. And if there is object and the touching here, and echoes are coming back to the part is coming back because of the after reflecting, this is also going in the radial direction everywhere. But the one part is coming to the your transmitter and receiver. In the receiving, when transmitting, no receiving. The transmitter is on, receiver is off. When the receiving the echoes coming from the object, transmitter is off. That is mean there is some interval to send into the radar beams. This is the radar pulses. We are calling the radar pulses. Red part is sending to the space, and if touching the object, then coming back to the part is coming back to the transmitter or the receiver. Okay, this is the distance they are recording because of they know that this pulse is sending time recording here and the receiving time is recording here. Therefore, the round trip going to the object, coming back to the receiver, then recording, then the time difference we can identify by the system and calculate the distance by using the velocity of the light. And that is how the distance are calculated, because of the speed of the wave, 3 multiplied with the 10 to the power 18 meters per second. 3 multiplied with 10 to the power 18 meters per second. This is the velocity of the light. Then you know the velocity, you know the time difference, sending and receiving. Then calculate the round trip distance and divide by 2. This is the distance is coming. Okay, that is how the distance are coming and then locating the objects. Okay, the targets may be different kind of targets. The aircraft, ships, spacecraft, that is the satellites, automotive vehicles, and astronomical bodies, including Earth, or even birds, insects, and the rain as well. We can use the radar to detect the objects, this kind of any objects. Besides determining the presence, in addition to the determination of the object, we can find out the location and the velocity of the object, whether the object is moving or not. And radar can sometimes obtain their size and shape as well. For in both cases, imaging radar or non-imaging radar. Non-imaging radar is not producing map. Imaging radar is producing the two-dimensional map or two-dimensional image. Okay, this is the radar, definition of the radar. And what distinguishes radar from optical and infrared, because we are the normal remote sensing, we are using the optical part, visible light, plus infrared. The sensing device, they are designing according to the this range of wavelengths, and ability to detect far away object under adverse weather condition. What is the difference? The radar from the optical and infrared has the ability to detect the object far away under any weather condition and to determine their range, distance with precision. And very accurate distance we can measure by using this one. This is the like the same as a total station in surveying. You can send the beam to the target, and reflected one is detected by the total station, and calculate the time difference between the sending and receiving, then calculate the distance. Total station, in addition to the distance, they are calculating the bearing of the line, then they can calculate the two-dimensional coordinates of the target, especially in the three-dimensional coordinates. The same thing in this one. The radar is an active because of we are not using the illumination source coming from the outside, because of the sun using for the optical and infrared, because of the illumination source is coming from the outside the system. But here illumination by using the microwave. Who is generating the microwave? This is a satellite or the aircraft or the drone or any platform. They are generating the microwave and sending to the space and finding out the object. Therefore, they are not using the illumination source coming from outside. Their own source of energy they are using, so that this is called active. It is typically operates in microwave region of the electromagnetic spectrum. This radar system is using the generating not light, they are generating microwaves region waves and send into the space to find out the targets. Okay, you may be familiar with the microwave, which is because of the weather forecasting you can see in the your TV news. This is the radar image. This is normally gray image. This is they are defining different weather condition in different places. This is the high in the red, here in the middle in the yellow, and so the not dangerous weather in the this is green and the blue. So that this is the weather image taken from the radar. This is the microwave oven. You can use to cook your food and heat your food as well. These are the microwave we are using, the well-known use of the microwaves. In radar system also we are using the microwave region of the spectrum. What is the microwave region? You can see the region here, 1 millimeter to 1 meter wavelength. You can see this is the 7 divisions of the electromagnetic spectrum, starting from the less wavelength to the higher wavelength, or inversely proportional to the frequency. Therefore, higher frequency to low frequency here. Low frequency to here is more than this is the high frequency to the low frequency. Okay, correct. This is the hertz, gigahertz. This is the terahertz. Okay, like this, these are the units we are using to higher order as well as the lower order wavelengths, nanometers, millimeters, meters, kilometers, and megakilometers, and like this going here and go in other direction, nanometers, then picometers, then femtometers, like this. There are different kind of meters. Here 1 meter, here this is the 10 to the power minus 3 of meter, 10 to the power minus 3 of the meter. This is 10 to the power minus 6 of the meter, or 10 to the power minus 3 of the millimeter. Sorry, this is the 10 to the power 6, because in between there is a micrometers as well. Meter, millimeter, all are going with the 10 to the power 3 minus 10 to, this is the meter, this is the 10 to the power 3 millimeter, 10 to the power minus 3. This is the micrometers, 10 to the power minus 6. This is 10 to the power minus 9 of meter. Then this next one is the picometer, 10 to the power 12. And then the pestometer, next one is the 10 to the power 15. Like this, you can go through the internet and you can go what is the 10 to the power 3 times meters going up, ascending order, or going down, descending order, what are the units. Okay, I forget now what is this. This is the tera, this is the giga. This one is not pisco, pisco is coming from here, going down part, going high part, or there is the different name here. Okay. However, all are coming from the 10 to the power 3. Okay. Okay, this is the photon energy is coming the electron volts. EV means the electron volt. This is the, you know, the volt in the current. This is the electron volt. This is the energy unit of the energy, electron volt. You can go through the equations with the what is called frequency multiply with the wavelength. These two multiplication is equal to the velocity of the light or the speed of the light, multiplication of the wavelength and the frequency, and the energy is coming the Planck constant multiply with the frequency. Then you can find out the photon energy. Then you can go through the previous lecture and combine together. You can find out the how these is coming together. Okay. Okay, that means that, for example, 390 nanometers wavelength is equal to the 790 terahertz frequency. Combined with the speed of the light, you can find out. However, in the microwave region is normally called from 1 millimeter to 1 meter. This is the part of the radio wave. Radio wave is 1 millimeter to kilometer. This is the 1 meter to 1 millimeter to 1 meter part of this one, where the high frequency part. This is the complete radio wave. Radio wave, the high frequency, this area is here, 300 gigahertz to 300 megahertz, part of this one. This is called the microwave, or the region found at the higher frequency end. This is the higher frequency end of the radio wave. Radio wave is 300 gigahertz to 3 hertz. In between, in 300 gigahertz to 300 megahertz is some part here, high frequency. Therefore, this is the high frequency part of the end of the radio wave. Okay, however, radar normally we are using 1 meter to 1 millimeter to 1 meter range. Okay, sensors are designing to ability to detect any number of in between these two numbers. Sensors are designing This is normally in radar system, we are calling the sensors as antennas. Antennas are designed to absorb the ability to any number in between 1 millimeter to 1 meter. Okay, I will explain later on how it is. Okay, different wavelengths of microwave provide different information to scientists, same as the optical system. In the optical system, if there is one sensor here, they are detecting different part of the electromagnetic spectrum. This sensor is detecting different part of the electromagnetic spectrum. Therefore, different information coming to this sensor, other different information is coming to the other sensor. So that in the microwave region also, different wavelengths provide the different information from the particular one object. The particular one object reflecting 1 millimeter wavelength in different way, 1 meter wavelength in another different way. The same object reflecting 1 millimeter wavelength in different way, 1 meter wavelength in another different way. Therefore, some object can reflect 1 millimeter wavelength, other object cannot reflect 1 millimeter wavelengths. One object can reflect 1 millimeter wavelength, other object cannot reflect 1 millimeter wavelengths. Then what is happening? You can differentiate these two if we are using 1 millimeter wavelength. If we are using the radar antenna 1 millimeter wavelength, then one object is reflecting, other object is not reflecting, then you can differentiate these two objects by using that kind of antenna. Because this antenna is designed to absorb 1 millimeter wavelength, but if we are not reflecting, this is not absorbed. Therefore, dark pixel will appear. 1 millimeter is reflecting by one object, very bright pixel will appear. Therefore, you can separate in the image bright pixel and dark pixel separately. Okay, these different wavelength subregions are called the microwave bands. If we are dividing the 1 millimeter to 1 meter wavelengths into the different subregions, okay, these are called the microwave bands. Bands of frequencies or bands of wavelengths in the microwave spectrum are designated by letters. But normally in optical system we are saying the blue band, green band, red band. We are not using any letters. We are using the band 1, band 2, band 3, band 4 numbers we can use. In addition to that, we can use the blue band, green band, red band, near infrared band, middle infrared band, far infrared band, thermal infrared, like this. But in radar remote sensing, radar region, we are using letters to describe the different kind of bands. We are using the letters, English letters, to describe the bands. Unfortunately, there are several incompatible bands designation systems. There are different kind of organizations are defined in different way. Therefore, they are using the different English letters to designate the what is called the band, microwave band. Therefore, there is some incompatible. Sometimes we get the confuse of this one. Sometimes these are doing purposely because of the security reasons, especially in the United States. They are using the different kind of letters and changing time to time, sometimes to get the confuse of the enemies. So that is why different organizations are using different letters. If you are using A, B, C, D directly, okay, one band is A, other band is B, other band is C, in the ascending order of the microwave 1 millimeter to 1 meter, you can identify what is A. If you know the A, you can know the B, the next to A. C is next to B. Like this, you can directly identify the region. But one band is, you can say band L, the next band is C, next band is X, then you can get confused what is L, what is C, what is X. Not this is the continuation of 1 millimeter to 1 meter, but you getting confused because why you are using L, why you are using C, why you are using X. There is no any abbreviation or anything. They are just using the different names. That is the problem for letters using here. Even within the system, not only the different systems, within the system, the frequency ranges corresponding to the some letters is different, somewhat between the different application field. Okay, they are inside the one system, within a system, some frequency range intersection with the other frequency one. Okay, for example, 1 millimeter to 10 millimeter, one band. Other band is 8 millimeter to 15 millimeter. Then 8 to 10 is intersection part. And that is also the problem. Now, because of the 1 to 10 millimeter is called the A band, 8 millimeter to the 15 millimeter is called the B band, then A and B are intersection somewhere. Therefore, if we are using A band for the different application, B band also can be also used for the same application. Therefore, people are getting confused. This is happening actually because of the World War II. The system is origin from the World War II, the top secret US classification of bands. They are using the band L, band C, band P, band S, band X, band K, the different names. But all are continuously going from the spectrum, no any gaps. But L, X, C are not combined alphabetical order, so that is the problem. Therefore, if you know the band L, we don't know what is the C. We are thinking C is some kind of less wavelength than the L, because in the alphabetical order L is going far away, C is at the beginning. Therefore, we are thinking C is lower wavelength, L is a higher wavelength. Like this, getting confused. Okay. One sort of microwave frequency band designations by Radio Society of Great Britain is called the RSGB. Is tabulated there. You can see this one. This is the L band. This is the what is called the RSGB, Radio Society of Great Britain. They are using L band is 15 centimeter to 30 centimeter. If you are calling of the wavelengths, yes, and the frequencies. 15 centimeter, 30 centimeter. This is called the military telemetry, using for the GPS, the mobile phone, GSM, the amateur radio. Okay, like this, this is the application users. But here the S band is 7.5 to 15 centimeter. The next one, going down here, starting from 30, then 15, then 15 to 7.5. Frequency is increasing 1 to 2, 2 to 4. Okay, then 7.5 to 3.75. C band. This is the continuously going 30 to 15, 15 to 7.5, 7.5 to 3.75. If you are using ABC, automatically you can identify directly what is A, what is B, what is C. But you can see this is the band L. There is no point why we are using L. Just use. This is the S. This is the C. Then you can see the next one is X. Because going down here, this is going here. C from X. 30. This is the 3.75 centimeter means 37.5 millimeter. Same, huh? This is millimeter, this is centimeter. This multiply with 10. Going to the 25 millimeter. Then again K going back. Here going down 25 to 16. So you can see different bands, a different application. But here you cannot see the only coming up to here the radar here. All other communication. But normally C band is also using the radar. L band also using for the radar. But after designing this one, later on they forget what is the letter for what this band, what is the range for L band, what is the range for S band. Only they can identify K bands, because others are forget, because not using this one. Because of the World War they are using the K band. Only they know the K band. Others are, somebody is asking what is S band, they don't know what is the region. What is the region of wavelength? Okay, that is the confusing for the enemies with this one, because when we are normally in the war time in Sri Lanka as well, the forces are using different kind of languages to give the messages for the frontline or battlefield. They are not using normal language. Same thing they are doing here. There is no any relevant, no any point why we are using L, why we are using S. Just use it. These are the band Q, U, V, W, F, D. So going down here, but you can see F is coming again, D is coming again. They forget everything later on, but they know only K band here, because for World War they are using for the communication and the radar detection. Okay, this is the what is called the Radio Society of Great Britain, using designing these names. Okay, these are there are a number of organizations that assign these letter bands. The most common being the Institute of Electrical and Electronic Engineers. This is IEEE. You know very well this one is normal, your paper publications is a very well very famous organization. This is Electrical and Electronic Engineers, Institute for IEEE. The radar bands followed by the North Atlantic Treaty Organization, NATO. The radio bands and International Telecommunication Union, ITU bands. There are different methods. You can see the what is happening if you are combined all together. You can see this is the IEEE, this is the NATO. The NATO is using A, B, C, D, E, F, G. You can see. Later on, they agree to this one, but later on again they are using the form 1. You can see the high frequency, very high frequency, ultra high frequency, UHF. This is the L band. In the IEEE, this is called the D band. The confusing in if satellite is saying that we are using the what is called DLM band. Okay, for example, they are using the band L here in the satellite. We don't know this is the region of this one or this is the region of this one. And this radar satellite is using the L band. According to the IEEE, this is the range is this one. According to the NATO, this is the region. You can see again, this is the intersection part here. You can see FD combined together. Here D is coming from here to this place, but here D is coming from 1 to 2 gigahertz frequency. Therefore, slightly different. Therefore, we should identify the satellite is using which kind of designation system is using for the radar antenna. Okay. This is the all to combine together NATO, IEEE and the ITU, International Telecommunication Union. They are using this name. Very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, extreme high frequency. Okay, like this. This may be THF, or you know what is this. Okay, same thing we are using here, but this is the LS. This is the IEEE using here. This is the NATO using here. You can see the all to combine together. What is L in the IEEE is equal to the D in the NATO, and UHF is equal to the NATO band here. Okay, you can see normally in the radar remote sensing we are using this kind of bands LSCX K, but B and W and the millimeters are not using. We are using LSCX. In addition to that, we are using the P band is inside the UHF. Okay. These are the normally imaging or non-imaging radar. We are using the frequency bands for radar remote sensing. As you know, in the normal optical remote sensing, the bands are using the range of electromagnetic radiation. For example, if we are calling the blue band, you are using 400 nanometers to 450 nanometers for one sensor. This is the blue band. Green band, you are using the 510 nanometers to 570 nanometers. That means that sensor is ability to detect 510 to 570 nanometers all wavelengths. If you are using one sensor here, this sensor is a blue band in optical remote sensing, 400 nanometers to 440 nanometers means that sensor has the ability to detect 400 to 440 nanometers all radiation incoming to the sensor. After reflecting from the ground, all wavelengths can be reflected, but that sensor is only detecting 400 to 440 nanometers wavelengths. This is the blue band. If we are designing the green band has 510 to 570, that sensor detecting only incoming radiation between the wavelengths 510 to 570 only. There is some range for the one sensor, but in microwave there is no range. Microwave antenna can generate, microwave transmitter can generate only one wavelength. For example, only 1 millimeter wavelength. They cannot generate 1 millimeter wavelength, 3 millimeter wavelength, 5 millimeter wavelength. They cannot generate, only generating one wavelength. Therefore, that antenna or sensor has the ability to detect only 1 millimeter wavelength. Okay, for example, if this is the C band, C is wavelength is 7.5 to here. Okay, we can take easy one. If we are taking L band, this L band is 15 centimeter to 30 centimeter. This is the band name L. If the satellite is using the antenna or the transmitter to send the 20 centimeter wavelength, this is the L band. That satellite is generating 20 centimeter wavelength and receiving 20 centimeter wavelength. this antenna has the ability to only send in 20 centimeter wavelength and receiving only 20 centimeter wavelength. This is the L band. This is the L band antenna. If the satellite is using, this antenna is using 17 centimeter wavelength generating and send it to the ground and receiving only detecting 17 centimeter, 17. That is also the L band because L is in between 15 and 30. So any number we are taking here to design the antenna is called the L band antenna. If any number in between this one, this from 7.5 to somewhere 4 here, this is C band. Only one number can generate. Like optical remote sensing, there is no range. Only one wavelength they are designing, they are generating and send it to the ground, and the antenna has the ability to sending that kind of wavelength only and receiving also that kind of wavelength only. If any number is using in between this one is called the L band. Okay, clear? Okay, radar system can be roughly divided into two categories. Imaging radar techniques. This is called the imaging radar. And non-imaging radar techniques we can use. Non-imaging radar is a type of radar system that does not produce the traditional images like those you might see in the typical radar display. Normal radar display, you can see the image, but they are not producing this kind of image. But display is okay because of the radar is seeing, antenna is seeing the area, you can display, but images are not producing. Instead of creating detailed visual representation of objects, non-imaging radar focuses on extracting specific information about the targets. It detects. A radar antenna is directed into the space and sent into the radar beam with one wavelength, then touch with any object, then detect it. If there is no touching, no object is detected. And after detecting this one, you can find out what is the direction this is going, what is the speed, what is the distance, what is the size, or any properties or characteristics they can detect. First, they have to touch with any object. Touch, then you detect the object. This is called the detecting the object. Then after detecting the object, you can find out the object is coming to the antenna direction or coming back, going away from the antenna direction or going no other direction. What is the speed? Everything they can calculate. They are not producing any map. This is called the non-imaging radar. Non-imaging radar systems are often used for specialized applications where traditional imaging radar may not be necessarily in practice. Non-imaging radar systems are often used for specialized applications, not normal for the traditional image, creating of the traditional image. Okay, one example is the speed measurement. Non-imaging radar systems are commonly used for measuring the speed of the moving objects, such as vehicles on the road or ships at sea. You can see nowadays rarely they are doing. Early days the police is detecting the speed of the vehicle in the straight road. Nowadays they are doing in the Kakira Anuradhapura road. But here not because of the curve road, it is difficult to detect, but straight line roads, they are detecting the speed. If a town area, we can go only the 50 kilometer per hours. But more than that, they can detect it by using the equipment, by using the radar. This radar system can provide the accurate speed measurements without the need of detailed image, not necessary to image capabilities, only detecting the object and finding out what is the speed. Okay, this is, for example, in the not here, this is in the foreign country. You can see. Okay, this is one of the developed country, but I don't know when it is coming to the Sri Lanka. Even now, nowadays, Sri Lanka is using the handheld machine to find out. That is slightly difficult because if we are using the hand with the equipment, hand is also moving. Therefore, this moving and the object is also moving, so that the antenna and the object both are moving. Then sometimes maybe speed can be reduced, or sometimes speed can be maintained. The max, added to that. That is the problem for hand using. We have to fix the hand, and we cannot move when we are finding out the vehicle speed. That is the problem. We can argue with them sometimes. We are going the 50 kilometer per hour according to our speedometer in the vehicle, but your hand is moving. That is why coming is more than 50. So when we are going to argue, that is a problem for Sri Lanka. I don't know what's happening. Okay, this is the Doppler radar actually doing there. What is the Doppler effect is? You can identify very clearly explained by that video. You can go through again and you can identify what is the Doppler effect. This is the other one is the Doppler radar is a type of non-imaging radar that measures the velocity of the object. Same thing, based on the Doppler effect. Doppler radar is commonly used in the weather forecasting to track the movements of precipitation and server weather systems. Also using this one. This is the radar. You can see this one in the Katnayak and Ratmalani airports. These are the radar antennas. Mostly these are using for military purposes. Okay, that one is the one, another application Doppler is using. Then you can go through again and identify what is happening actually, the waves theory. This one and the previous one. Then the another application is a collision avoidance. Avoid the vehicle, okay, when we are crossing the vehicles, sometimes there is an accident can be happen, it's a collision of the one vehicle to the other one. Then this can be avoided by using the radar system. Because some vehicles, some cars has, if you are close into the other vehicle, automatically stop. In Sri Lanka is also some vehicles are here. When you are driving here, when the people are going across the road or the vehicle is coming closer to our vehicle, it's automatically stop. Automatically the brake system is working. Okay, this is also the radar system. This is the non-imaging radar system often used in collision avoidance systems for vehicles, aircraft, and marine vessels. This radar system can detect a nearby object and provide warning to the operators to help prevent the collision. Okay, this is also, you can see how. That is how the vessels are going to avoid the another vessels in front of that one. They are looking for how avoid this one with the collision of this one, because of this one is coming from here, this one is going here. This is normally in the, you can see if you are doing the mathematics, if you did the mathematics in advanced level, you can know the relative velocity. And this is the method they are going to apply for this one. Now you can go through again and again these videos, you can identify what is actually happening. One time it is not clear, sometimes you can go to the two or three times, you can understand what is happening. Okay, remote sensing also the another application which we are using here, non-imaging radar. Because of the, we are looking for in optical satellite system, we are looking for the remotely sensors to identify that. In addition to that, there are several other sensors inside the satellite. We are looking only for blue band sensor, green band sensor, red band sensor, infrared band sensors like this. But in addition to that, there is altimeter, spectrometer. There are several things there to direct to the sun direction. Because of the solar panels should be always in the sun directions. And to identify the altitude of the satellite, there should be the altimeter. This is the using the radar system, radar altimeter, non-imaging. They are not preparing image, but finding out the altitude of the satellite by using the altimeter. Okay, there are different kind of sensors we are using in the satellite system by using the microwave to identify the different kind of other parameters necessary for the satellite moving. Okay. This is the non-imaging radar is also used in the remote sensing applications such as monitoring the movement of glaciers, and the measuring ocean currents and detecting changes in the terrain elevation as well. In addition to the height determination, some other sensors they are using to identify the different kind of things. Okay, this is a non-imaging radar system, our equipment we are using to find out the vehicle speed. As I told earlier, vehicle is moving. If hand is also moving, the speed can be sometimes reduced, can be sometimes increased. We don't know. Therefore, this should be the fixed. This should be the fixed. This is the Doppler equation. This is the frequency the person can get. This is the frequency of the what is called the source antenna. This is the different velocities. This is the velocity of the light. This is the velocity of the object. This is the velocity of the source. Then you can find out if vehicle is going here, closer to this one. Therefore, frequency is high. For this person, frequency is getting low. The frequency is getting low, this will be the minus. Frequency is getting high, this will be the plus. And by using this equation, you can find out what is the frequency hearing of that this person. The vehicle have the siren here. Okay, also this one you can find out. This is the Doppler method we are going to apply for non-imaging radar system. This is vehicle collisions problem. If this one is very close, then they are given the first one, the radar detects the slower the vehicle ahead. This one is slower the vehicles ahead. System provides the audible and the visual warning. Third one is that the vehicle automatically initiates the braking to avoid the reduce the speed of the collision. Okay, this is what is the collision warning. This is the finding out the ocean surface height. Because of this is going the wave because of the tides in the sea. Therefore, you can find out the difference in the tides. Therefore, accordingly, the surface current, different kind of things you can get from this kind of sensors. This is the altimeter measurement system. Okay, these are the 4 applications in non-imaging radar system. What we are doing here in the microwave remote sensing is imaging radar system. The non-imaging radar system, another one is you can see in the as I told earlier, they are not producing the two-dimensional image or map, but display. They can display the maps as well as display the objects seen by the antenna. So this is one is the plan position indicator. This is in the plan view map, objects surrounding it, the rotating antenna. You can identify what are the objects around it. Normally this is this kind of PPI is establishing in the airport to identify the aircrafts coming to the airport and going away from the airport. They can identify. This is normally using for the air traffic controlling. Okay, this type of system is commonly in the weather forecasting, air traffic control, navigational application, and not appropriate for remote sensing application. In our case, because of this is not very good for the images because of the poor spatial resolution. Because of they have the poor spatial resolution. Because of the large field of view, therefore at a time, instantaneous field of view is very large, so that 1 pixel is sometimes maybe when the target is touching, this resolution will be 1 kilometer by 1 kilometer or more than that. Okay, so that this is not good for the imaging system, but remote sensing, non-imaging radar. Okay, this is the, you can see the field of view. Field of view is very large. Then you can see the object detected. If somewhere, if object is there, they can detect it. The first time they detected in this place. Second time, if this one is detecting in other place, then they can see this object is coming to the antenna direction, or the object is in here. Next time, this is going away from the antenna place of the antenna. So that is how the air traffic controlling is doing. Okay, then we are coming to our part. This is the imaging radar. Imaging radar is an application of radar which is used to create the two-dimensional images, like optical image. Imaging radar provides is light to illuminate an area on the ground and take a picture at microwave. In optical remote sensing, sun radiation are coming to the ground and detecting by the sensor. But here, sensor or the antenna provide the light by using microwave and send it to the ground, and detecting the going back part to the antenna direction. Other part is going to the other direction after interact with the ground, scattering in different direction. Part is going back to the antenna is called the back scattering. Okay, microwave is generating by the satellite system, the transmitter, and send it to the antenna. Antenna is sending to the microwave as pulses to the ground and touching with the ground. This is called the interact with the ground and scatter in different direction. This is a reflection in different direction. And scattering part is going back to the antenna is called the back scattering, detecting by the antenna, the same antenna. That is what the imaging radar is doing. Then recording on board, pixel by pixel. That is we'll explain later. Okay, these are the radar images. This is the airborne radar images used in the aircraft because with the high resolution, because of the low altitude. This is the spaceborne radar. This is the airborne radar. This is the spaceborne radar. Because of the high altitude, they have the low spatial resolution, like many dots. In radar image, one can see only the energy because of the wave. Wave contains the energy. Wave has a frequency, wavelength, energy. Energy is measuring by the number of photons. Photons is going to the energy, with the energy, then touch with the ground, energy reflected back. Part is back towards the antenna in recording. Okay, this is the example of the radar images. Okay, different micro bands for imaging. These are the imaging we are using band, P band. This is in between 30 to 100. This is the ultra high frequency area. You see the gigahertz 1 to 0.30. Okay. This is the P band. This is the 100 centimeter means 1 meter. 30 centimeter to 1 meter. Because of the 100 centimeter is equal to the 1 meter. This is the longer wavelength. Longer wavelength has a low frequency. Okay, next one is L band. 1 to 2 frequency. High frequency, lower wavelength, 30 to 15. centimeter. If any satellite antenna is using 75 centimeter wavelength, this is P-band. If any satellite antenna is using 90 centimeter wavelength, this is also P-band. If some satellite is using 35 centimeter wavelength, this is P-band. Any number of wavelength in between this one, only one wavelength they can use, is called the P-band. Any number in between 15 and 30, they are using the L-band. But 30 is common here, but you can go this one for this one or this one, no problem. Okay, next one is the S-band. Frequency is 2 gigahertz to 4 gigahertz. Wavelength is 15 to 7.5 or 7.5 to 15. You can call anyway. If you are saying the 30 to 100, this is the ascending order. 100 to 30, that is the descending order. 15 to 30, ascending order. 30 to 15, descending order. You can call anywhere, any method, no problem. And this is the C-band. This is the most popular band using for the imaging radar system. 3.8 to 7.5. Then the X-band, 2.54 to 3.8 centimeter wavelength. Then Ku-band. Ku-band, this is 18 to 12.5 frequency, 1.7 to 2.4 wavelength. This is the Ka-band, 40 to 20.6, 26.5, 808.12. There is in between there is a K-band, you can see 18 to 26.5, 18 to 26.5, there is a K. Because K is using for the World War II, they are divided into two bands. One is called the K upper band, the above band, this is the under one. Because K is coming 18.0 to 40. The below part is using the Ku band, above part is using the Ka band. This is the normally using for the non-imaging radar, but sometimes they are using for the different kind of images. Okay. These are the normally microwave bands we are using for the imaging system. This is the Ka, not very useful for the SAR. SAR is synthetic aperture radar. I will explain what is this later on. SAR means synthetic aperture radar. You know the aperture of the camera. Aperture is synthesized. Synthetic aperture radar. Other one is the real aperture radar. Real aperture means real antenna size. Synthetic aperture means real antenna is using, real size is using, but they are working as a different size. This is called the synthetic aperture. The real aperture is antenna size, length of the antenna. Synthetic aperture means the same antenna using but working as a very large antenna. This is called the synthetic aperture radar. That will explain when we are coming into the RAR and SAR. Okay, this is not very useful for the SAR. Therefore, using the airport surveillance, they are using K-band, or you can see the intermediate K-band. This is 18 for 26.5 here, the intermediate one K-band. Because full K-band is divided into three categories: Ka, 27, 2730. Earlier you can see here. 80 Ka band, 26.5 40, 27 for 40. Ku is 12.12 to 18, here 12.518. in between is the K, balance K part. But all are using airport surveillance and the World War. They are detecting the aircraft and different kind of kafir and so many things. At that time, we don't know. Okay, this is the X-band, high resolution, low penetration. Because of there's the ability to microwave has the ability to going through the clouds, going through the any weather condition. But X-band has a low penetration, not useful for vegetated areas. When we are coming to the application, we'll see what is happening. Typical application: urban and infrastructure monitoring, ice and snow monitoring, and weather forecasting. Also, C-band, the medium resolution, medium penetration, mediumly going through the clouds, higher coherence. Coherence also I will explain when we are coming to the high coherence means relation, higher relation. This is using for the change detection, ice, urban and infrastructure monitoring, maritime navigation and glaciers. In the S-band, experimentals are they are using synthetic aperture radar, the research areas, high penetration, agriculture monitoring, marine radar. L-band, medium resolution again, high penetration. Because the wavelength is increasing, higher penetration of the areas. Geophysical monitoring, biomass and vegetation mapping and the soil moisture content identification. P-band, high wavelengths, 30 centimeter to 1 meter. This is also the experimental and susceptible to ionosphere, no sensors yet decided. Biomass, tropical forest mapping and the soil moisture. They are using for as like a non-imaging radar, but still they are using the no sensors for the imaging. But non-imaging, they can identify the different kind of things by using this one. Okay, this is the P-band. Okay, these are the different microwave bands for imaging. Okay, these are the various satellites because we are talking about the satellite remote sensing. So that we are using the various satellite employed with the SAR imaging with the different years here. This is a 2025 here. This yellow color is a L-band. You can see the very small one is in the P-band. You can see here biomass, only one here. All others are L-band, X-band, C-band and S-band satellite. Okay, these are the different kind of satellites available, presently available and previous satellites as well. This is also the mission and the agency also is also given. Green one is the past and still flying one. Blue one is a mission approved. Yellow one is a mission planned but not funded. This is the 22. This is the map for the 2021, not 2024. We don't have the 2024. What's happened for this mission? You can check with the internet. This is a satellite of a NISAR satellite. This is Indian remote sensing. You can see, go through the internet and what is happened to this satellite. You can check. You can check what is happened to the because of the 2024. This one is mission approved. Already sometimes maybe launch the satellite. Sometimes still the problem. You can check with the internet. For example, you can type the NISAR satellite, present situation of the NISAR satellite in the Google search. You can identify. Even in our Sri Lanka satellite name, you can type What is happening now? Our satellites, 2 satellites are there. No, we don't know. You can check. This is not the radar, but these are the optical satellites, telecommunication satellites. You can check where the satellites are now. Okay, imaging radar. There are 2 kinds of thing. One is the airborne, other one is the spaceborne imaging system. Are using microwave sensors called the radar imaging system. Why radar? Works day and night. You know the advantages of this one. Works all weather. Can provide very accurate distance measurement. Can measure velocities, moving targets. This is especially need for the volcanoes and earth movement, earth slides like this. This is important one. Is can measure the velocities, can measure the movements. Not only the radar system. This is we can use the radar interferometric techniques to find out the earth movement. Okay, this is the application. This is the why the advantage we are using radar system. Okay, you can remember that there are 2 kind of system. In imaging radar system, one is the airborne, other one is the spaceborne. Okay, this is the radar antenna, how it is working. This is the transmitter. There is a circular switch here. When the transmitter is on, receiver is off. Transmitter is on means the radar pulse is sending. This is the radar pulse sent into the ground by the antenna. This is the antenna. Transmitter sent into the generate in the microwave. Okay, that will come later. I will explain. This will generate the microwave and send into the antenna. Switch is on, then send into the antenna and send into the ground. At that time, no receiving. Then after that, switch is off for transmitter and switch is on for receiver, and receiving after reflecting from the ground the previous pulse. Before this pulse, the previous pulse returning is coming here and recording and come to the receiver and go to the recorder and processing inside the pre-processing sum on board and coming to the display or after receiving here on the ground. Okay, then after receiving, then switch off for the receiver, then switch on for the transmitter, and the next pulses are sending. There is a pulse duration. This is the front of the pulse. This is the rear of the pulse. Pulse is touching the ground here, front, and directly touching here until the end of the pulse. Until the end of the pulse, this one is touching the ground. Then receiving from the ground. Then the receiving time is the receiving from the ground, some strip on the ground. Then for the next pulse is scanning next line. One pulse is scanning on one line, next pulse is scanning next line. When the next pulse is scanning, satellite is moving one line in the flight direction. Radar pulse is touching the ground, and after completing one line, satellite is continuously moving to the next line. Then the out of focus from the first line, then coming into the focus of the second line. At that time, second pulse is coming to the ground, and returning is starting from the second line and receiving by the same antenna, where the switch is off for the transmission. Then after this line, out of focus, the satellite is going to the next line. Then the next pulse is sending, receiving is off. Then next pulse returning signal is starting to going back to the antenna, then switch is on for the receiving, off for the transmission. Like this, line by line is scanning and recording here. Okay. How many pulses are sending? 1500 pulses are pulses per second. 1500 pulses per second are sending to the ground. That is pulses sending time interval and the satellite speed are combined together. Normally, because of the next pulse is going after how many seconds, that is depending on the satellite speed as well, because the satellite should be focused to the next line. Satellite should move to the next line. Otherwise, satellite is not focusing to the next line. So that satellite speed, pulses sending speed, all should be interrelated. Sending high power pulses about 1500 pulses per second. That is depending on the different satellite speeds. Pulse having the duration typically 10 to 15 microseconds. Here the duration is 10 seconds to 10 microseconds to 50 microseconds. After 10 micro, if this is the duration is 10 microsecond, after 10 microsecond this pulse is finished. Therefore, pulse duration means, if there are pulse duration means there is a pulse length. Because of the duration time, according to the speed of the light, you can find out what is the pulse length of the pulse. This one multiply with the speed of the light, then you can find out what is the length of the pulse. Pulses are sending in fixed frequency. As a 1500 pulses per second, all frequency are same. This is called the pulse repetition frequency. Pulse is repeating first time send, second time send, then time difference between the first and second, same as the second and third, same as the third and fourth. This is the pulse repetition frequency is same. Intermediately there is a interpulse duration. Pulse duration is there. Pulse duration is 10 to 15 microseconds. Pulse repeat the pulse, one pulse to the next pulse. There is an intermediate time difference is called the interpulse duration. At the interpulse duration, the receiving is going to the antenna. Pulse duration, touching the pulse on the ground. Interpulse duration, return signal is recording in the recorder. The receiving at the receiver. Transmitted pulses interact with the material on the ground and scatter. Come to the ground, pulses are coming to the ground, interact with the ground and scatter in different directions. Sometimes some part can be absorbed as well. That is depending on the ground material. Okay. This part of incident energy reflected back towards the radar antenna depends not only the surface material roughness and its dielectric properties, but also on other factors. There are different factors, different characteristics on the material on the ground. There are all factors are depending how the touching microwave is scattered. If it is smooth, like a mirror, signal is coming to the touching to the ground and reflected away from the antenna. No reflection going to the antenna because of the like a mirror. This is the smooth surface. If it is rough, it scatter in different direction. What is going back to the antenna? This is called the backscatter. Okay. Okay, this is how it is working as I explained earlier. Red part is coming to the ground and touching, going back to the green one to the same antenna. Do you need the interval or going continuously up to 330 or do you know the interval or not? Okay, I will give the 15 minutes interval and then we'll come back to the next place. Okay.
Okay, sir.
Recording stopped.
Okay, I will come back within 15 to 20 minutes. Okay, yes. Hello, welcome back. And can you hear me?
Yes, sir.
Hello,
Sir?
can you hear me and can you see the screen?
Yes, sir.
Okay, thank you. Okay, now we stop here and then we'll go to this is the radar, how it is working. And this is the transmission echo time of pulses determine the platform target range, distance from the platform to the target. Okay, this is the transmission echo time of the pulse determines the platform target range because of the transmission time and the receiving time both are receiving by the antenna, so that they know the transmission time, actual time for the round trip. So going to the ground and coming back to the antenna. Therefore, according to the speed of the light and the time difference, then you can calculate the distance and divide by 2 is the distance from the platform to the target. Now, this is easy, like total station same, but GPS is slightly different. GPS is sending the message from the GPS satellite. The receiver is on the ground. Then you are receiving the receiving time is recording by the receiver. Sending time is recording at the GPS. There is a time synchronization for the GPS and the receiver. It's not the same because of the GPS clock is atomic clock, very high, accurate and precise. But which the receiver we are using, for high accurate receiver, this is a good clock, but there is a time, some time difference. That is why the 4 satellites is necessary for to find out the what is called the 3-dimension coordinate. Because of the 3-dimension receiver XYZ, we have to find out. Only 3 satellites is enough to get the 3 equation to solve for the 3 unknowns. But there is a one additional unknown is coming because of the time synchronization of the GPS satellite and the receiver. Therefore, 4 unknowns are there. Therefore, to resolve the 4 unknowns, we need the 4 equations. To get the 4 equations, we need the 4 satellites. That is why minimum 4 satellites are necessary for the finding out the coordinates of the point by using the GPS receiver. But here there is no problem because satellite is sending the signal and receiving the same satellite, same antenna, so that the time can calculate. There is no any additional time gaps between sending and the receiving. Therefore, very accurate distance can be calculated. Okay, then the echoes received by the antenna are converted into the digital data and passed to the data recorder for later processing and display as an image. The echoes are received by the antenna, then convert into the digital number. That is the strength of the signal. 100% strength is coming. This convert is to the 100. If 50% is strength energy is coming, then convert it to the number 50. If no signal is coming, then convert into the 0. But this is the 0, 50 or 100. 50% is coming, 50, 100% signal is coming, 100%. No energy is coming, 0. Let's convert into the 100, 50 and 0. Actually, that is not 100, 50 and 0. That is converted into the, according to the radiometric resolution. If the radiometric resolution of the image is 2 to the power 8, this is the 8-bit image, 100 is converted to the 255. 50 is converted to the 127. 0 is converted to the 0. That is how the optical satellite system happens. because of the sensor receiving the 100% of energy, 100% of energy according to the sensor wavelength range. All wavelengths are coming 100%, then convert to the 100, but if it is 8-bit image, the maximum number is 255 is convert. 50% is coming 127 or 28 convert. Like this, according to the radiometric resolution of the image, they are converted to the 100% to the higher number of the radiometric resolution. 0 is the 0. Like this, the echoes received by the antenna are converted to the digital data and converted as an image. Okay, these are the four main components. Same as earlier I explained. The transmitter, receiver, recorder and processor and the display. Then all explanations are here. Transmitter is used to generate the microwave signal and transmit the energy to the antenna from where it emitted towards the earth surface. Transmitter is sending to the through the switch, they are sending to the antenna, then antenna is sending to the ground. And the receiver accepts the backscattered at the ground, which is back to the antenna. This is backscattered. Sending microwave is interact with the ground, scattered in different direction depending on the ground material and the wavelength, and the part is going back to the receiver or the antenna, same antenna, then recording. The filters and amplifiers, it has requires for recording. That is what we have done. Or filters mean then after touching the ground, 1 millimeter wave, they are sending back the 1 millimeter, sometimes maybe more than less millimeter or higher millimeters. But only filtering is 1 millimeter by the antenna, because antenna is sensitive for 1 millimeter. Then 100% 1 millimeter signals are coming, then convert into the high number of the radiometric resolution. This is they are using filters and amplifiers to convert the relevant digital number. Recorder is store the received signal pixel by pixel. One radar pulse is using for recording the one line pixel by pixel. One line pixel by pixel. Then the next pulse is next line, again pixel by pixel recording. Antenna alternatively transmit and receive the particular wavelength. Transmit, then receive, then transmit. This is the alternatively transmit and receive the particular wavelength. Then high power pulses per second are transmitted to the direction of interest, target which the antenna is looking, or the area to be imaged, with each pulse having the duration. This is called the pulse duration or pulse length or pulse width. Because of the duration, there should be a length, because of the velocity and the duration. Duration is a time, there is a velocity of the pulse or the speed of the pulse, therefore there is one object with the speed and the time duration, there should be a length, distance, because distance is equal to the velocity multiplied with the time. If there is no acceleration, this is the constant acceleration, then the duration, if there is a duration, there is a length because of the speed is there. Therefore, SC is equal to Vt, or D, different kind of notations are using. And then another name is called the pulse width. Width is the length, same. These pulses are emitted with the fixed frequency, pulse repetition frequency. First pulse, then the second pulse, third pulse, the fixed frequency. First pulse after 5 seconds, second one. After 5 seconds, for microseconds, third one. After 5 microseconds, fourth one. Like this same fixed peak. This is called the pulse repetition frequency. Each line of the image represents the strength of the signal returned from the single radar pulse. One pulse is using to scan one line on the ground. One pulse is using to scan one line of the pulse of the ground. This is called the swath width of the ground. One pulse is using to scan the one line on the ground. This is the swath width. Strength of the signal returned to the single radar pulse converted to the digital number, as I told earlier. After completion of one line, next pulse is transmitted with the platform moving along the flight path. Intermediately, before the second pulse, after the first pulse, then receiving part is doing by the antenna. Intermediately moving the satellite and the flight direction for the one line is scanning. Then the adjacent area is illuminated. This is the adjacent line, and the antenna receives the backscatter from that strip. That makes the next line of the image. By repeating this continuously, radar images are produced. Line by line is scanning using the pulse by pulse. Then the primary radar, there are two systems. Microwave, the radar system are divided into two, imaging and non-imaging. The imaging system is divided into two parts. One is the side-looking airborne radar, we are called the SLAR, and the synthetic aperture radar, this is called the SAR. The SLAR system, side looking, this is the special thing, side looking. This is also the side looking. Side looking airborne radar and the synthetic aperture radar, also the side looking. Normally, SLAR is based on side looking airborne radar is a real aperture radar. Real antenna is using. This is called the RAR. Real aperture radar, and the SAR is using in the spaceborne system because of the high altitude. The short antenna is sending large field of view. Okay. The large antenna is sending very sharp and radar beam. Okay. If antenna is going up airborne to spaceborne, the short antenna sending the large field of view going up, altitude is high, very large. At a time they are looking a very large area. Therefore, spatial resolution is getting fine or not. Spatial resolution is getting very weak, not the fine resolution. Okay, large size of the pixel size is large, mean resolution is decreasing. Pixel size is increasing, resolution is decreasing. Therefore, large field of, therefore if we are using the short antenna in the spaceborne, the spatial resolution is very weak. Spatial resolution is decreasing. So that we cannot use the very small antenna. Therefore, we are using very small antenna but working as a large antenna. Because of the large antenna is sending very sharp beam. Very sharp beam with the very high altitude, we can getting very fine resolution, spatial resolution. Therefore, short antenna is working is a very large antenna is called the aperture is synthesis. Aperture is synthesis. This is called the synthetic aperture radar. Again, I will explain when we are coming to this fishbone radar. Okay. Both system is a side-looking configuration. Whether it is RAR, real aperture radar, or synthetic aperture radar, both have the side-looking configuration to eliminate right-left ambiguity from two symmetric equidistance points and to get the better range resolution. Okay, this is the antenna here. This is the exact vertical direction, and this is the nadir point according to the photogrammetry. We can say this is the touching with the ground. This is called the ground nadir point. This is the track, nadir track, where the antenna is flying. Antenna is going the perpendicular to the screen here. Perpendicular antenna is, the satellite is moving perpendicular to the screen and side looking. Then the swath strip is not along the nadir track, but in optical satellite system, directly they are looking the orthogonal direction. This is the nadir point. Satellite is moving perpendicular to the screen here, looking the exactly orthogonal direction. Sun radiation are coming, looking this area. If what is happening, if this radar antenna is using here and looking orthogonal direction, the radar pulse is coming like this and touching these two places at the same time. Because of this is the center, this is the radius of the curve. This is the curve, pulses are coming as a curve. This is the center, this is the radius. Therefore, both are equal here. Therefore, return signal going from here and going from here both at the same time. Then both signal from this object and this object going to the antenna at the same time. Therefore, antenna cannot identify the signal is coming from the left side or the right side. Both are same. This is called the right-left ambiguity. Therefore, this pixel and this pixel are at the same place. To avoid this one, we are side looking. If the signal are coming like this, radar pulse is touching here. Until the end of pulse is going touching from here to this direction. Pulses is touching here and going here, but no problem because going here because the satellite is also moving to this direction. At that point, after this point, satellite is out of focus in this line. So coming to the next line. The next pulse is coming, starting from here, going to here. The satellite is moving for the third line. Then the next pulse is coming. Next line is scanning. Pixel by pixel is scanning. This one and this distance are different. The very close distance are different. This is called the range direction. This is the ground range. This is the range direction. We are looking for the ground. This is called the ground range. These are called the slant range. I will explain when we are coming to the geometry of the satellite radar satellite system. That is why, in addition to that, this one and the next one is very close to this one distance. Not like this. This one and this one is slightly different. But here very close. Therefore, to differentiate this distance and this distance, the very large distance on the ground should be come. Therefore, all return signal in this area are going together. Therefore, pixel size is very large. Therefore, in this case, if you are using the radar system, left-right ambiguity should be avoided and the range resolution should be very poor. It should be fine resolution. We have to make the side looking. That is why the radar system is side looking. Satellite is moving perpendicular to the board and looking the side, not directly orthogonal looking. To avoid the left-right ambiguity and get the best range resolution. Resolution in this direction is called the range resolution. Resolution in flight path direction, other direction perpendicular to the board, is called the azimuth resolution. This is the flight direction is called the azimuth direction or along track direction. Flight path is coming perpendicular to the board is called flight direction, along track direction, azimuth direction. All are same. This direction is called the range direction or a cross track direction. This is the along track direction perpendicular to the board. This direction is called a cross track. This is the crossing the track. Track is perpendicular to the board, a cross track direction. Therefore, this direction is called a cross track. Perpendicular is called the along track. Along track, flight direction, azimuth direction. This is the range direction, a cross track direction. This angle is called the look angle. This angle is called the look angle, perpendicular to the what is the looking direction, the look angle. This is the range now. This range is called the slant range because of the side looking. But the image is in the ground range. Image is in the ground range. But the recording in the slant range. Because of the recording to this point and this point. Because of the same, this distance and this distance are same. Because this one is recording here. Therefore, recording data is in the slant range. After, when we are going to process, we have to convert to the slant range to the ground range first. Okay, that will come in the processing. Okay, this is how these parameters I will explain again when we are coming to the geometry of the satellite. Okay. Aircraft or spacecraft platform moves in the uniform speed and altitude. This is precise because of the ground monitoring stations always looking the spacecraft. Aircraft can uniform altitude, uniform speed, but altitude sometimes may be problem because of the photogrammetry. Flight can be rotate in different 3 directions. Flight can move in the flight direction can be changed. Flight direction can be changed in the 3 ways. This is called the kappa p omega in photogrammetry. I will explain when we are coming to that place. Aircraft taking the one photograph and the second photograph, there are 2 different places the 2 photographs are taking in the aerial photogrammetry. Therefore, flight is in the first place and the second place is can be differentiated in 3 ways: rolling, pitching, and other one is I forget the name. But the aircraft directions can be changed in 3 ways. Okay. The antenna is fixed below the platform, same as the what is called optical remote sensing, and directed to the side, not orthogonal, not nadir direction. Commonly perpendicular to the track. Perpendicular to the track. This means the track is here, directly looking side and perpendicular, but here. Not perpendicular vertically, but side looking and perpendicular to the track. Okay, I will show in the diagram. That is called the squint angle is 0. Squint angle is 0. Okay, this is the forward motion of the platform provides the scanning along track, azimuth direction, right direction, along track direction. Forward motion of the platform is the aircraft or the satellite provide the scanning along track. The beam is wide in the vertical direction and intersects the surface in the oval with the long axis extended in the across-track direction. When we are using the beam, that will not come though. Normally in the optical satellite system, sensors are designed by using the charge coupled devices, CCD. The CCD chip is square type charge coupled device. But when square type of charge coupled device is looking the ground with the high altitude in the space-borne satellite, space-borne system, this pixel is not exactly square. This is the circular type. You know the if you using the torch with the square face, if you are using the light is not coming the square, light is coming in the oval shape, round shape. Therefore, when we are seeing the charge coupled device from the space, square charge coupled device, but looking area will be not square, this is the oval shape. But when we are displaying in the computer, this pixel is coming as the square. Okay, this is how the beam is wide in the vertical direction and intersects the surface in the oval shape. And the long axis extended across the track. Okay, we will see the diagram, we can see. Thus digitizing the signal in time provided scanning in the range direction. Then range direction, pixel is going here, from here to here. This one is going, this pulse is going from here, scanning starting here until here. This one is coming as a oval shape. But oval shape is one pixel is oval shape, other pixel is oval shape, but totally this one is coming as a oval shape. This one is slightly larger than, wide than this one. Because of this distance is greater than this one. Because this is the far, this is the very near. Therefore, oval shape is coming like this. Okay, then time to time, this line is scanning. This is digitizing from this place, next place, like this separation. According to the separation, how it is separation, that is depending on the resolution in the range direction. How one pixel is separated by the other pixel, that is depending on the resolution in this direction. According to the resolution, then the pixel by pixel is scanning, but final one is coming as a oval shape area. Okay, this is how happening. This is the scanning how, but this is the strip. This is the nadir point is here. The strip is going slightly side. This is not only from the one satellite, this is the two scanning. For interferometry, they are identify the earth crust. Small changes of the earth surface is identification. That is why different kind of combining together, different kind of colors are coming. This is actually the interferogram generation. Okay, this is the complete geometry description. Okay, this is the flight path. Satellite is moving here. This is the nadir point, nadir direction, exactly vertical. Then the antenna is side looking, perpendicular to this flight path. This one is perpendicular. And the side looking. This is the nadir track. Flight path, azimuth direction, along track direction. Nadir track. In your optical remote sensing, this strip is coming in the nadir track. Center is the nadir track, both sides same. This is your scanning area, but this one is a side. Okay, this is the look angle, gamma. This is the beam width. Antenna is sending the beam. This is the beam width in azimuth direction. This is the looking area first, and this is the pulse are sending here. First pulse is coming here, touching here, and until this one is coming. You can see this is coming as a oval shape. Near range, this is small. Far range, this is called the far range. This is the near range. This area is larger. This is the pulses are coming. This is the front of the pulse. This is the rear of the pulse. This is the radar pulse. This is a slant range. This one is the ground range. This is the ground range. These all rays are slant range. This is the resolution in the slant range. R. This is not the complete pulse. This is the one pulse. This is the other pulse like this. This is the radar pulses, not the pulse duration. This is the slant range resolution. This is the ground range resolution in the range direction. This is the resolution in slant range, resolution in ground range, resolution in azimuth direction. This is the swath width. Okay, this is what is called normal. This is the satellite altitude. Satellite altitude H. Theta is the incident angle. Incident angle is this is the this is the ray coming to here. Okay, this make you are using the perpendicular line to the ground, vertical line to the ground. This is the incident angle. This is the incident angle in the far range. This is the incident angle if you are using the perpendicular line here. This is the incident angle near range. If you are using the perpendicular line here, this is the incident angle of far range. This is larger than this one. Incident angle is increasing from near range to far range. Incident angle theta is increasing from near range to far range. Okay, these are the normal parameters in the geometry of the what is called radar satellite system. Okay, this is ERA satellite. You can see the same. These are the pulses are coming. The first line is scanning by the one line. The next line is scanning. The next line satellite is moving this one. Next, this pulse is scanning next line. This pulse is scanning third line. This pulse is scanning fourth line like this. This is the beam is a width in this direction, light direction. Beam is width. Beam width is called beta. That is why this one is called the beam width. This is defined by wavelength divided by the antenna length. Normally azimuth beam width, azimuth direction, beam width is defined by lambda divided by L. If the lambda is fixed for the particular system, one wavelength, L is increasing, beam width is decreasing. To go into the space-bound, same L, okay, this one is the same, but height, according to the height, this one is getting very large. So that is why we are using the SAR system in this direction. I will explain when we are coming to the SAR. Nadir track, azimuth direction, flight path, what is the other one? Azimuth direction, along track direction, cross track direction, range direction. In between these two special thing, interpulse duration, interpulse period. This is the pulse duration. This is the front of the pulse. This is the back or rear of the pulse. this is the toe. This is, we are using the Greek alphabet is a toe for the pulse duration. This is the interpulse duration. This is pulse duration. This is interpulse duration. All are same. Interpulse, all are same. Pulse duration, all are same. But the interpulse and the pulse duration are not same. That is the difference. Okay, this is called the footprint. Okay, this is the geometry of the it is called the satellite. I will explain again when we are coming to the design. Okay, now the new thing is coming, the spatial resolution, real aperture radar, and spatial resolution in the synthetic aperture radar. There are two independent system parameters. One is the pulse duration or pulse length, and then antenna beam width, lambda or L, determine the ground resolution cell size. Okay, one by one I explain by the next lecture. Okay, I will conclude this one for the this one. I forget to record this part. Sorry for that one. I forget to record this part, but okay. However, if there is a recording somewhere, I will explain again. Okay, don't worry. Okay, I will stop now for today. Then spatial resolution. This is going to slightly complex one to explain. That is why I stop here. And I will starting from the spatial resolution in range direction and the azimuth direction. The two-way I will explain. Okay, I will stop for the today. And thank you. If you have any questions, you can send through the email. If you have any questions you want, you can send the email. Who is Veer Surya? Please send if you have the group already established in the WhatsApp, please send me. I will make a new group for the 5206 GS. Okay. Okay, thank you for today, and we'll lecture 3 for the next Sunday. And thank you.
Thank you, sir.
Thank you, sir.
Yes, sir.